All right, everybody, welcome to the video here for the answers shown for the Algebra 2, June 2022, parts 2, 3, and 4. We're going to try and go through these kind of quickly, see how you're doing here. You should be checking your work here. We're using this as a video to kind of review a concept. So, number 25 says, does this have imaginary solutions? So there's two ways to determine whether or not something has imaginary solutions. Right? If it's quadratic, right? We can look at the graph. And the graph will have no x-intercepts. Or the discriminant will be less than 0. It really doesn't matter how you do it for this question because it just says, does it, and to justify your answer. So justify your answer, remember, means just like show some type of math. So like you could literally just sketch a graph of this like this and say there are no x-intercepts. So the equation has imaginary solutions. If you chose to use the discriminant part, you would just say like negative 4 squared minus 4 times 1 times 13. Type that in, see what you get. It's a negative number. Pretty sure it's a negative number. Let's see. Desmos. So we have negative 4 squared minus 4 times 1 times 13. We get negative 36. Same thing. All right, it's imaginary solutions because of that. All right, next it says the initial push of a child's swing causes the swing to travel a total of 6 feet. Each successive swing travels 80% of the previous distance. Find the total distance of this geometric series. The geometric series formula is the first term minus first term times r to the n, all over 1 minus the r. Now, in this case, to get from one term to the next, we're going to multiply the previous term by 0.8 because each swing is 80% of the previous swing. So like a sub 1 would be 6, a sub 2 would be 6 times 0.8, and so forth and so on. So if we type in here for the total amount of swings, how many swings is it? It is 5 swings. So we're finding the sum of the 5 first terms. So we'd say the first term minus the first term times 0.8 to the fifth, all over 1 minus the first term. Type that into your calculator, and you get 29.99. Next one, we need to make a common denominator. Common denominator is n squared, so I'm going to change that middle fraction to be n squared by multiplying the top and bottom by n. Then I'm just left with the exponent, the numerators as my equation. And I can do some quick algebra here to solve. We also know that n can't be 0 because that would be my undefined values. Since n is not 0, that's my good answer. We're good, and we move on. Number 28 is a factoring question. We could attack this problem a lot of different ways. I'm assuming since most of you saw it was 4 terms, you jumped right to grouping and you ignored the fact that there's a GCF of x in there, which is okay. But I'm going to take out an x first. So I'm going to take out an x, leaving me with 2x to the third plus x squared plus 18x minus 9. I'm then going to do my grouping step. So I'm going to group these two together. See that x squared is common, leaving me with negative 2x plus 1. I don't want to just take out 9 here because I won't have negative 2x. I'd have positive 2x. So I'm going to take out negative 9, give me negative 2x plus 1, meaning my factors so far are x, negative 2x plus 1, and x squared minus 9. And I can still factor our good friend difference of two squares. That's going to become x plus 3 and x minus 3. Moving right along. An independence test. I guarantee you there's going to be an independence test somewhere on your Regents exam, whether it's in part 1, 2, or 3. If I'm asking you for independence, you have to show me one of three things. So you can say probability of one event is the same as that event given a secondary event. Or you could say the probability of the events both happening is the same as the product of the two events happening individually. Or you can say the probability of the second event and test is not the same as the second event given the first event. Doesn't matter which one you use here. So they're talking about blue eyes and wearing glasses. So I'm going to do the probability of having blue eyes, and I'm going to test, is that the same as blue eyes, given that you wear glasses? Well, the probability of having blue eyes would be this whole row, which would add up to 0.40. The probability of blue eyes given wearing glasses, well, given wearing glasses is this column. Well, that whole column is 0.35 if you add it all up. And there are 14% that wear glasses out of that. So that'd be 0.14 over 0.35. If you divide those two numbers, guess what you get? You get 0.40, meaning these are independent. Notice it just says justify, not explain. So you just have to say independent. Show me math, tell me an answer. If it says explain, you'd have to tell me what it means. Next one. Next one wants us to see if these two things are equivalent and determine the value of A. So right away I say a cube root. I don't like that. I'm going to make it a exponent of 1/3. And then each exponent, including the one on the 81, gets an exponent of 1/3 to it. 15 times 1/3 is 5. 9 times 1/3 is 3. So I've already made these two things the same. So in reality, all I really care about is that this and this are equal to each other. So off to the side here, I can say 81 to the 1/3 is equal to 3 to the A. Well, to do this, I want to make that base of 81 into a 3. So we know that 3 to the 4th power is 81 because I played with my calculator and I saw that that came up. So I get 3 to the 4th can replace 81 to the 1/3 is equal to 3 to the A. Then using the power to power rule again, I can multiply 4 and 1/3 and get 4/3 is equal to A. That'd be the easiest way to do that one. Next one, a nice little sine or cosine curve. Cosine curve here, right? So we have an amplitude of 2. We have a midline of 5. 1, 2, 3, 4, 5. Make my little dotted line for midline. Go up 2. That would be at 7. Go down 2. That would be at 3. Now the 1/2 is the frequency. And we remember that period times frequency equals 2 pi. The frequency doesn't really help me graph. The period does. So knowing the frequency will allow me to find the period. So the period is going to be 4 pi. So I'd go out my 4 boxes, I'd make 4 pi, and then I'd chop it up. That's 5 boxes, counting is hard. 4 pi, and I'd chop it up into 4 equal parts. Now this only wants us to graph the 2 pi, meaning I'm not going to see an entire cosine curve here. I'm just going to see half of it. Because if this is 4 pi, 2 pi is only going to be here. Now, since it's a positive cosine curve, we know the positive cosine curve starts at the maximum and then follows its pattern. So we go maximum, midline, minimum, and we make our curve, and that's all we need to show. Next one, we just did regressions, and remember we could do this right on our calculator. So I'm just going to show you how to do that real quick. So add a table. In the x1 column, we're going to put our x values, so 0, 5, 10, 15, 20, 25. In the y column, we'll put our numbers, 180. Let me just make sure I don't make a mistake here, 144, 120, 104, 93.3, and 86.2. Then go down to line 2, and we want to put in our regression equation. So y1 squiggle a times b to the exponent of x1. Remembering to click log mode, and we have our a and b parameters given to us. So now we just have to round appropriately. That's it. Use the correct variables. So f of t is equal to 169.136.971 to the t. Don't put x. All right, next question is another graphing question. So if we graph f of x in our calculator, we're going to get some coordinates that we can graph. -1, -4, 0, 0, 1, -2, 2, -4, and 3, 0. And we can graph our cubic. It's going to come up, turn, and come back up, label like IF. We can also graph -5, 1, 2, 3, 4, 5, up 2 to the right 2, use your slope, use Desmos, whatever you're doing to graph this. And we have G. The next part, the number of solutions, not what they are, just how many. How many solutions are there? There are 1, 2, 3. That's all you got to show for that. Done. Number 34 talks about this pendulum moving back and forth, all this good stuff. Gives us T for time, L for length, and it gives us in the first part here a length. This is L. So all this is asking you to do is to plug in L. So 2 pi times the square root of 67 over G. They tell us what G is, 9.81. Type that in your calculator, and you get 16.4. Second part was the hard part. So it says the time is 9.6. It's still going to be 2 pi. This time I just don't know L. So the algebra involved here is first you got to get rid of 2 pi. So since it's multiplied, I'm going to divide by 2 pi. So I get 9.6 over 2 pi is equal to the square root of L over 9.81. I am not even going to type that in the calculator. It's going to be a messy number. Just leave it. Square both sides. So we get 9.6 over 2 pi. Still not typing it in the calculator is L over 9.81. To get L by itself, you multiply by 9.81. And now we have L. Type this into the calculator, and you get an L value of 22.9. That's it. Number 35, you probably recognize from your stats test. I put this on the last stats test. So it gives us a simulation. The margin of error we're going to do first, and we'll talk about why the answer to the second part is no. So first off, as soon as I see mean and standard deviation over here on the simulation, we're going to use those numbers to make our confidence interval. So our margin of error is going to be 2 times 0.034, which is going to be 0.068. So we're going to add and subtract that to the mean of all the dots. So our confidence interval, or plausible interval here, is going to be 0.651 plus or minus 0.068. So our confidence interval rounded to nearest hundredth is going to be 0.58, comma, 0.72. Now this confidence interval is the interval that we're confident the percentages of the people that drive to work. Now, they want to know if after launching this campaign to get people to stop driving to work and take public transportation, if it was effective or not. So the simulation found that this was our confidence interval, but the sample, right, our p hat, is 122 over 200, which is 0.61. That is in this interval. Because it's in that interval, it wasn't an effective campaign because it was comparable to the results that we had before the campaign. Now, I know you might be looking at it and saying, well, the original sample was 65% and it went down, but it didn't go down enough to become something that we would consider a statistically significant change. A statistically significant change would be outside of the margin of error confidence interval. So this answer would just be no, because the p hat is within the confidence interval. Number 36, fully expect a system of equations to be somewhere in parts 2 or 3, most likely in part 3, because it's a lot of work. Sometimes it's a circle line like this one, sometimes it's a 3 by 3 system, sometimes it's a parabola in a line or a parabola in a circle. It could be any combination of those things that we did in class. So I'm going to take the linear equation and solve it for y. So I have y equals 2x minus 5, and I am going to do some substituting. I'm going to replace that for y. So the equation I'm going to try and solve is x squared plus 2x minus 5 squared equals 25. Now, as soon as I see 2x minus 5 squared, I'm going to make boxes. That's going to give me 4x squared minus 10x and positive 25. So I can rewrite that as x squared plus 4x squared minus 20x plus 25 equals 25. Clean that up a little bit by combining some like terms and moving this to the other side. Well, that's factorable using our good friend GCF. And then I can set each of these equal to 0. And I get x equals 0 and x equals 4. Now, if you did all that beautiful math, great, but you're not done because we want a system, so we want the x and the y values. So I'm going to use the linear equation that I solved for, and I'm going to plug in 0. That's going to give us negative 5. And I'm going to plug in 4, which is going to give me positive 3. So my coordinates are 0, negative 5, and 4, positive 3. Now, if you want to check this, or if it was part 1, you could just graph it. There we go. So we could graph x squared plus y squared equals 25. And we can graph y plus 5 equals 2x. And we can see that these two things intersect at 0, negative 5, which we saw, and 4, 3, which we solved for as well. Last but not least, we have this recursive sequence being defined for us. So we know that 92.2 is our original value. We see it's geometric because there's a common ratio, right? So our R is 1.015, right? They want us to identify the percentage of annual growth. So the percentage of annual growth is going to be this R value, which is 1 plus our growth rate is equal to 1.015. So our growth rate is 0.015, which is 1.5%. Second part says we'll use this information then to write a function. So the population, P of t, is equal to the initial amount of people, 92.2, times the growth rate, 1.015, to the t. Everything's still in years, so we don't have to do anything crazy here. The last part was the hard part. It says, according to this model, I want to approximate how many years until we get to 300 million people. So I'm going to replace P of t with 300. And I'm going to solve. Well, to solve this, I need to use logarithms. Before I could do that, I have to get rid of the 92.2. So I'm going to divide it. That's going to be a weird decimal, so just leave it as 300 over 92.2. And we get this exponential part. So if we natural log both sides, ln here, and we ln here, the t comes to the front. So we're going to get the natural log of 300 over 92.2 is equal to t times the natural log of 1.015. All right, remember that t comes to the front. Then we can divide both sides by the natural log of 1.015. And we get whatever that comes out to in our calculator. Holy smokes. And we get 79 years. That's it. Hopefully that makes sense. Hopefully you got a lot of those right by yourself, and we're just using this to kind of help us guide through or check answers. See you soon.